It's some way to understand what these equations mean, because we're always given Navier-Stokes equations and told to look at it a particular way, and it always leads in the same problems. We have to use CFD, or we have to do these modeling things like this, and then we go down from there. So we want to change the question, okay? What are the questions we can tackle with CFD right now, and what is it that we cannot do, okay? And it turns out there's a lot we cannot do, and which is far more exciting than what we can do with CFD right now, okay? So that's what I want to discuss. Now, this is very, sometimes it's math intensive, you can think of it that way. These are also things that you may not have seen before outside in classrooms, so it might be a little jarring. So we'll go slowly. There are like 40 slides in this. I can use only 3 or 4, and that's good enough also. Yeah, so we don't need to go through all 40, okay? So the topic I want to look at is to think of these governing equations using dynamical systems, okay? And that's that's the main thing I want to look at. I've just arbitrarily put it somewhere here, but and this comes from certain problems that I look at, which is a precursor to what we will talk about tomorrow on high-speed flows and so on. We discuss high-altitude engine relight, where you take an aircraft to altitude, you have to show that it comes back up. And I told you, based on the boundary conditions, sometimes it can light, sometimes it cannot. So there's some variability to it. So in that particular case, that variability comes from the pulse discharge for the igniter, not really depositing all the energy, or the incoming turbulence, you really do not know the entire scope of it, right? So this is the main thing. But this was the start of trying to think about this problem differently. So now you have a system where even if the pulse discharge is all uniform, you have fully figured it out, the incoming turbulence, okay, has a binary impact on the outcome, right? So before, whenever we talk about turbulence, we said turbulence impacts the flame, it increases the flame speed, so you have turbulent flame speed, things like this. So it was never to the point where you have some inflow conditions, and sometimes you will have a flame, and other times you will not have a flame, right? So that was never the choice posed to us. It was always whether, how much variability it's there within some small value. So to give you context, we talked about turbulent flame speed, which is maybe like 2 to 3 times the laminar flame speed. This is what we saw yesterday. So this is a routine thing that we see, okay? But what if I set up a case and I light it up, and sometimes the flame propagates at 10,000 meters per second, and other times it propagates at 1 micrometer per second, right? So that's a huge variation in the outcomes. Now, if that happens, you cannot rely on that system anymore, okay? Now, fortunately, this almost never happens in combustion. You never have a flame that propagates that fast, things like that. It's always, somewhere in the middle. So which is why all of the statistical tools that we're using are very apt for combustion, because most of the variations we see are in a very narrow region. There's not a huge variability here. But this is not always the case, okay? And there are different ways to think about it. So I want to show this set of problems. If I can get the mouse to the right place. Yeah. So this is a typical problem in scramjets. And we'll talk about scramjets tomorrow. It's not very critical for the physics right now, but I'll just briefly explain what this is. What you see here on the right-hand side are simulations, unsteady flow simulations. The geometry looks pretty, you cannot figure out what it is, right? It looks, nondescript. We don't know what is a boundary, what is happening, and so on. So essentially, if you look at the left boundary, there's a flow coming in, and what I'm plotting here is velocity. And velocity goes between minus 250 meters per second to 750 meters per second. So which is, relatively fast. 750 meters per second at room conditions for air would be about Mach 2, Mach 2.5, something like this. So it's relatively fast, let's say. And what this sequence of pictures tells you is that there's a feature, and if you look carefully, that's the blue region. So the blue region tells you there's a negative velocity. Those are the recirculation zones. And as this simulation progresses, which is from the top to the bottom, that negative region starts to become more and more important in this field. Okay? So what it reflects is that there are shocks inside the system, and this is the flow that feeds into the scramjet combustor. And what you have here is that those shocks are slowly moving upstream. They're moving towards the inflow. And when they reach the inflow, the scramjet will fail. That's called scramjet inlet unstart. Okay, so this is what will happen. So here, it's moving slowly. In fact, it's moving very slowly. If your flow velocity is like 700 meters per second, that shock is going to move roughly at 10% of the velocity upstream. So it's moving at 70 meters per second upstream. Okay? So you cannot easily figure this out from these pictures, but typically that's what happens. It's a very slow motion. But at some point, it is going to fail. Okay? Now, when we do LES calculations, if you guys have done LES, you would know how this is done. If you're an experimentalist, this is what happens. You choose your favorite software. You figure out how to do this geometry inside that. You make a mesh. Then you have to specify boundary conditions. And you say that it's turbulent flow at some velocity or whatever it is. And then you have to specify unsteady inflow conditions, showing how the turbulence is varying at the inflow. You do the calculations, and you run it for some time until you reach steady state. And at steady state, you will collect averages, time average of the value. This is what you typically compare with experiments. So in the experiments, they would run, some case, they would measure. Oh,
can I make an announcement?
Yeah, sure.
Okay, I know it's very hot. I found you a new building, another building. Working perfect. Robertson Hall. I'm going to send you. Actually closer to Taipei.
We will go now?
No.
Oh, tomorrow. Oh, okay. Okay.
Robertson Hall across the street.
Perfect.
Actually close to Taipei. And nice and cool. Okay?
Thanks, Ed.
Okay.
That's useful.
Thank you for bearing, but it's cool down the heat.
Mm.
Too much. I won't work. Okay. All right. Not too bad.
Okay. I completely lost track. Yes, experiments, okay? So if you run this simulation, like a flame or something like this, you would run it for a long time. You will reach some kind of steady state where you see the turbulence, but things are not changing over time all that much. You will collect averages and you compare to experiments. And the experimentalists also would have done similar procedure. They would have started the experiments. They don't specify boundary conditions. They turn on meters or whatever they do. And then they measure stuff after some time. They collect averages. And then you compare your averages to their averages. And if they match, it's done. Otherwise, you go do more research, right? This is usually what we do. But these problems are different. There's something unsteady going on here. It's a transient flow problem where I run an LES calculation, and by some coincidence, I get a process that looks like what's happening on the other side, on the left, which is the PIV data, the velocity data, for an equivalent geometry. It's not identical, but it's almost close to this, okay? And there also they see similar things progressing over time. So you see the shocks progressing. But this is what has happened. The LES simulation is just one simulation that I've done, and the experiments are also one experiment that was done, one run, okay, in which they started an experiment, they did something, they induced this unstart, and then they watched it go back, they measured all of this, okay? Now, the question is, can we compare this single experiment, single run of an experiment with a single run of a LES calculation, okay? And of course, you can compare. This is a paper that we wrote, so you can always compare these two. Nobody stops you from that. But it's not mathematically correct, okay? So it turns out there's a way to think about LES that's more than writing equations, filtering them, and things like this. You can think of them in a way that's more mathematically consistent. And when you do, you will notice that this experiment and this LES, there's no reason for them to be equivalent at all. It just so happens they show similar features. But even this experiment, they should have run it hundreds of thousands of times, which if you're an experimentalist, you know it's not feasible, right? Maybe you can run 2 experiments or 3 experiments or 3 runs or whatever. But 100,000, no. And if you run a simulation like this, you're not going to run thousands of simulations either, okay? So then the question becomes, what is it that these simulations do? What results do LES provide and things like that? And this was not, this was not on anybody's mind at all for a very long time. But then it became more and more critical because LES was becoming very popular. They were using it for problems like, including myself, doing these kinds of comparisons. And now the question is, can you even make these comparisons? Okay. And then it's like an onion, right? So you peel one layer and there are more layers inside. So it turns out that it's a much more complex question than saying that can you compare them. So that's essentially what I want to discuss here, okay? So this goes to a topic called matching density. So we looked at probability density function, and this becomes the root for what we want to study here, okay? So we are trying to understand how to do this. And so one way to think about it is that each of these LES fields, or for that matter, LES solution, let's say you have 10 million grid points in your solution. At each grid point, maybe you have 20, 30 variables. So 10 million times 30 variables is 300 million points that you have, data that you have, okay? You can think of, we talked about PDF before, 30-dimensional PDF, okay? What you really need to think about is to take each one of these points, 300 million points, as an independent dimension. So you will have a PDF that's 300 million dimensions, okay? And if you do experiments, you'll have some similar quantity. And it's only these densities, these PDFs, that should match, not the individual solutions that you have, okay? So which is a more complex process than just saying, I'll run an LES calculation, I'll do an experiment and compare them. For steady state time independent problem, this is not an issue. You collect time averages, then it should be okay. So this is what started our idea about how to think of these systems. You must have seen this somewhere. You guys know what this is? You know what this is? Lorentz, but what Lorentz attractor? You guys know there are many Lorentz attractors, or Lorentz systems. This is a Lorentz 63. There's also a Lorentz 96, okay? So this is what starts the term, the butterfly effect, right? So it's very cringy, but if a butterfly flaps its wings in Brazil, then there could be a tornado or a hurricane in Florida, like what we saw yesterday, right? It's possible. But the idea that small variations in a chaotic system can lead to very large variations in outcome, right? So that's the essence of it. And if this is the case, you can now start asking questions that you have not asked before. And that's what we want to truly understand. So in this particular case, we always plot like this, and it's a very funny way to plot a result. So we are all used to plotting a temperature as a function of x and y direction, things like this. So in this simple problem, there are only 3 variables, not 300 million variables like what we have in LES, only 3 variables. And what these guys have plotted is the solution at every time for these 3 variables. So each of these variables will have some value. You plot them together, and it looks like this in this 3-dimensional plot. And it follows this very intrinsic trajectory that has 2 lobes, the left and right lobes, and the solution many times stays on the left lobe and sometimes goes to the right lobe, okay? And it transitions between the 2, okay? So this transition is important because, in our mind, if we think that the left lobe is the burning flame solution and the right lobe is the extinguished solution, let's say, then you can have a situation where, depending on where you start the problem or how long you wait to do something, you can either go to the left lobe, the fully burning solution, or to the right lobe, which is the extinguished solution. So how you start the solution, how long you run the calculation, all of this becomes important. The whole idea of treating each one of these variables as an independent dimension is at the basis of what is called dynamical systems theory. This is what used for control theory and for many other, for machine learning, all of these treats partial differential equations or ordinary differential equations as dynamical systems, and then you try to model them based on this. So we want to understand turbulence or turbulent combustion using ideas like this, okay, to ask questions that we cannot ask before. So what kind of questions can we ask? One example is this. So soot in an RQL engine, okay? So on the left is from Air Force Research Lab, I think. I forget the names of the authors. I should know, but I forgot. Mel Rockamore is one of the authors. So they built some combustor. They have a glass window. They just looked at it. So it's not like some fancy laser diagnostics. It's the simplest you can do. They just looked at it. Yeah. And whenever you see that white stuff coming out, that's soot. Okay. So soot is not always there. So it's not like a flame that it always sits there. It forms intermittently, and then it goes away. Okay. And so there is some time over which it needs to form. There's an incubation time, right? And then everything is wiped out, and then it starts afresh one more time. So this process repeats itself. Okay? So even though we think of turbulence as some kind of continuous perturbations, soot and these kind of features are very intermittent. So they are not there all the time. So if you now make measurements for a very short window, when there's no soot present, you will conclude that soot is not formed in this reactor. At the same time, if you average it for sufficiently long time, but you capture more of the times when there are a lot of soot, you will also inaccurately claim that there's a lot of soot being produced here. So now this becomes a very complicated problem. How long should you average it? What are the cycles of soot formation in this problem? Things of this nature, which we don't ask at all before. Now, on the right-hand side is the simulation. I'm at this point, I don't want to predict whether it will work or not. Will assume it's not going to work. But that's also a movie. And it will sort of show that when this mixer fraction is fuel to air ratio, right? When this fuel comes in, sometimes it breaks off as lobs of fuel. And it just sits there. And when this lob of fuel just sits there, very rich, in a high temperature region, it forms soot. And when it forms soot, that fuel after some time gets dispersed, it goes away, and the soot just stays behind. And that's what you see as white regions here. Yeah? So there's some kind of very long-term effect, even in this highly turbulent combustor, that normally if you do things like temperature measurements or species measurements, you won't care about any of this stuff. You just take time averages, and then you're done. It's all good. But there's something else happening here, right? There is a memory to the flow that you do not see when you just take time averages. Yeah? So this is very important. Many of these flows, they're not just highly turbulent flows. They also have parts of the flow that are not turbulent. For instance, there's recirculation zone, which is very low velocity. Okay, so it's nearly laminar. So every combustor is a combination of low velocity regions that anchor the flame and high velocity regions that promote fuel air mixing or other kinds of mixing to increase burning rates. Yeah. The low velocity regions have this peculiar habit of storing information for a long time. So they have a lot of memory. Highly turbulent regions have very short memory. So if a flow is very turbulent and you make any change to the flow, it will immediately get rid of that change. But if you have a very low velocity flow and you make any change to the flow, intuitively we can think about it, right? So it will take a very long time for the change to go away. So now we have a system where there's low velocity and high velocity regions, and you need to have a quantity. Temperature is not that quantity. You need to have something like soot or NOx that depend on that memory, right? And now you have a very different flow system. And then the questions now change. So can you predict how intermittent the soot formation is in an aircraft engine. Not just how much soot is produced, but how often is it going to get produced, right? And if you change the operating condition, what is the change in this memory effect? How is it going to change? So you have a completely different set of objectives for your simulations. So this leads to a math term, ergodicity. You guys have heard ergodicity or ergodic flows? No? Some have heard ergodic flows. Yeah? So what is an ergodic flow? So when the statistics do not change with time, I would call it statistically stationary flow, because the PDF is not time dependent in a way, right? Ergodicity is something more than that. You guys know? The time average equal, what does it mean? Time average is equal to ensemble average.
I think if you take either volume and average it, or if you take several times at the same point, it will give us the same average.
Somewhat, but it's not complete still. So it's in the philosophy of that, like you can translate two different averages, right? But the ensemble average, if you think of that soot experiment I said, you run the soot experiment from scratch millions of times, okay? Every time you run it for some, let's say 4 seconds. At the 4th second, you take a snapshot and you keep it. And you run it for every experiment like this and you average it. So that's an ensemble average. An ensemble of experiments, and you're averaging at t equal to 4 seconds, that average, okay? Now, I can also run only one experiment, but I run it for 100 seconds, okay? And I average the solution for 100 seconds. If that solution is the same as my snapshot I had from the ensemble average, those flows are now ergodic. Yeah. So you have to be able to repeat the experiments, and those should be the same as what you can do from time averages. Now, this is not most flows don't need to be ergodic. We can never prove that a flow is ergodic. That's not critical. But once you look at these kind of flows, there are a set of questions that arise that are more interesting than predicting average temperatures or how does the flame look like and things. Those are all very interesting, no doubt about it, but you can do one better than that. So this is a set of these problems. We already looked at some of them. That one is high altitude relight. So you take an aircraft to altitude, flame extinguishes, you try to bring it back to life. What's the probability that it will light up at those conditions, right? So which means that there's some variability. You cannot be sure it will light up, and you need to know that probability that it will light up, okay? And how do you do a simulation that will capture that probability? Not that you can do a simulation to compute probability. That's very different. I can always run calculations by changing stuff and come up with a metric called probability of ignition. But that has nothing to do with why a practical system exhibits that variability, right? So that difference is there. Or you can have something like an inlet unstart, where the shock moves forward, and I have to figure out how to predict that something is going to unstart, or what is the probability that it's going to unstart. But the most important question comes from the bottom picture here. So flame flashback. So this is, if you have any kind of gas turbine, this is something that's very critical. So you have a combustor, flame is located somewhere, and suddenly it decides to move into the mixing chamber upstream, especially for premix flame. This is deadly because you are not designed your mixing chamber to hold a flame, so it goes in, it burns down everything, right? So predicting flame flashback is a critical modeling requirement, right? And we work on this. There's a big challenge. People work on this one. Now, it's one thing to say when this flame is going to flash back, And maybe we can predict that. You can have correlations to say, okay, if my inflow conditions is like this and my equivalence ratio is that, then the chance of probability of flashback is high, and so on. That you can do. But the more critical question is to say, if a flame flashes back, what is the fastest velocity at which it's going to go back? Because it's turbulent, which means that its velocity is not the laminar burning velocity, so it can go at different speeds. But what is the fastest speed at which it's going to go back? Okay. Now, this might look like a simple problem. The immediate, if you do CFD, the immediate thought process is this. I take the same problem, I figure out how to induce flashback, and I run many, many simulations with small changes to the info, like I did for the relight problem. And you know what? I'll figure out what is the distribution of these velocities, so I will know what's the fastest based on that. Which it turns out is not true. If you want to prove that you can figure out the fastest velocity, the number of simulations you'll have to do will be the same as the number of degrees of freedom you have in DNS. So if your Kolmogorov length scale scales as Reynolds power -3/4, we saw this yesterday. So if you want to figure out what is the fastest velocity, what you have to do is some Reynolds power 9/4 number of simulations, and only then you can figure out or be sure that you can capture that PDF of velocity. So that becomes very difficult to do. So if the question always is, can you predict flame temperature or flame structure, to me that problem is solved. This is an industry problem right now. And if you go to industry, they'll give you tools like ANSYS or whatever tools you have, and then you figure this out because you need a practical solution for a practical problem. That's the focus of industry. If you want to do research that's completely different, you have to ask different questions. I'm not saying ask this question. This is my question, not yours. But you have to find your own question, right? And this is one of them. And if you pull this thread, then everything breaks down because all the tools that you've built are to answer the first question, how does the flame look? That's it. This is all we can do. But if you ask questions like how fast it's going to go back, you have no recourse at all. There's no method to look at this. Okay. So that leads to a whole set of problems. This is not critical. And that's based on what I call non-ergodic flows. And I'll come to this. The details of this is not critical, but these are the questions one could ask. So you can ask, what is the fastest velocity, which is very difficult. The easier question to ask is what is the distribution of flashback velocities, okay? And even that is an unsolved problem. You can also ask the more stringent question, what is the probability that the flashback velocity will exceed a particular number? And that's even more difficult. And there are no solutions to this right now. It's easy. The hard part is asking the questions, and then I just hope that my students will figure out how to solve them. But so far, I have only the questions, no solutions. Yeah. We have thought about it, and I'll show you how we have thought about it. But it's not there. We don't know how to do this methodically. So the whole thing starts, and I don't want to go into the nitty-gritty details of it, with this very basic notion. We talked about LES, and we said to get to LES, we take DNS field, we filter it, and we get some LES field. And the LES field is more smooth, and so we can use coarse mesh to solve it. This is our whole hypothesis. Okay? Now, I reverse the question. I give you a LES field, okay? Whatever you want, all the species, everything, but only on the LES field. And I ask you to construct a DNS field out of that LES field. Know that the LES field does not have the small scales, right? So you have to do something to construct the DNS field because you don't have that information, okay? Now, much of what we do is somehow implicitly assuming that if I give you a LES field, there exists exactly one DNS field that I can get from this, exactly one of them. We don't know how to construct it, but this is sort of also our assumption. But it turns out it's statistically not valid. If I give you partial information, there are many ways to complete that information. So I can, in fact, construct thousands of DNS fields. When I filter each one of those fields, I'll get the exact same LES field. Okay? Now, each one of those DNS fields is going to evolve a little differently because they're all different in some small way. So they're going to evolve a little differently. So at a future time, each one of those DNS fields is going to be different. Okay? Now, this is what I can do. I take all those DNS fields at a future time. I now filter each one of them. Okay? And I can be sure that all those filter fields will not be the same. So I start from one filtered field. I construct thousands of DNS fields. I evolve all of those DNS fields. I now filter them to get back an LES field, and I find that each one of those LES fields is different. So the modeling construct we have somehow has to account for this. And that's the root of how we think about LES modeling now. So from, when we were doing this in the 80s and 90s, this was driven mostly by lack of compute power, coarse resolution, and how do we close those models? We assume that we are doing this, we're committing the sin by cutting off at a filter width. So what do we do to correct for it, right? That was the idea. But it turns out that's the wrong question overall. Because if you take any LES field, there are many, many ways it's going to evolve. So what are you trying to model? What is it that you're trying to reconstruct with your subfilter models? Okay? Which is not very obvious. Now, there are people who have solutions for this. One of the solutions is given there. You say, I'm going to construct LES models such that if I take LES field, construct all these DNS fields, at a future time, I get different set of DNS fields and several LES fields. What I want to do is that my original LES field has to reach the average of all those LES fields I have at a later time. So my models have to follow that constraint. Okay? And there's no way to internalize this and build it from scratch like we do for dynamic procedures. So people have resorted to machine learning or things like this to build it. Okay? But to directly construct this model is not so obvious. Okay? But this is one way to think about this. Now, I'll skip this part. This is not critical for now, but I'll go to the main idea of what I want to discuss. It's also very hard, so I would prefer not to talk for another 20 minutes. So I'm a chemical engineer. So if you do chemical engineering, you have to learn process control, which is like control theory for aerospace engineers, but it's for operating plants and things like that. And so we always take whatever our equations are, we make them into dynamical systems. We do all of this analysis based on this. So to me, it's very natural to think like this. But it's not all the time. This is not how we are taught in aero or mechanical and so on. So the best way to think is you take Navier-Stokes equations, you discretize those equations. So in mathematical terms, the Navier-Stokes equations are infinite dimensional. They're partial differential equations. And you make it finite dimensional by discretizing those equations. And when you discretize those equations, for every grid point, there is an evolution equation, which comes from the right-hand side. So you can say velocity at some grid point, the rate of change of velocity at that grid point is equal to a right-hand side that involves a lot of other terms from other points on the grid and so on. That's your finite difference or finite volume discretization. So for each point, you have an equation. Each variable at each point, you have an equation. You put all of them in a giant vector. That's your psi on the left-hand side, the bold psi. And on the right-hand side is n, which is your Navier-Stokes equation written in terms of all these discrete variables. So I've taken what is a nominal partial differential equation and converted into a large system of ordinary differential equations. So that's this expression right here. So I give some initial conditions. There are some boundary conditions that are automatically included in the discretization, and then I can solve this problem. Okay, so d psi by dt is n is all of CFD. This is what we do for every problem. Now, if you look at turbulent combustion and you want to do DNS, that psi is very long. Typically, I said 10 power 9, but many of the problems we do now, there are about 10 or 20 billion grid points. There are maybe 30 species in them. So it's getting close to 1 trillion degrees of freedom. So it's about 10 power 12 variables inside. That vector is 10 power 12 length, right? So it's pretty long. So when I solved this problem, you saw the Lorentz attractor, which are 3 variables, and I could plot that nice shape that comes from this. I have 10 power 12 variables. There's no way to plot it, right? I don't know how to plot more than 3 variables at a time. So this is not something you can visually analyze, okay? Now, this is why thermodynamics is important. Now, brute force, yes, this is 10 power 12. But what happens is that heat release is so dominant and everything is pushed towards this thermodynamic equilibrium as fast as you can, these variables collapse. So that map I showed for the Lorentz attractor is for 3 variables, and you get an attractor that's sort of low dimensional. It's in 2 dimensional. It's like a flat plate in 3 dimensions. That's how it looks. The same way for combustion problems, even though the original system is in 10 power 12 dimensions, because that's the number of variables, it quickly condenses into a much smaller set of variables that control the entire problem. If you use flamelet models, that variable set is only one, mixer fraction, right? If you use equilibrium, if you use flamelet models, mixer fraction and dissipation, there's 2 variables. But that's only for the flamelet part of it. It's not for the CFD part of it. But you can think of it the same way. You have 30 species, you have reduced it to 2 species. You have 10 power 12 variables, you can reduce it to a much smaller dimension because thermodynamics forces everything to live in this much smaller volume, okay, in this space. So this was a, in the 1980s, this was a big push. People understood that once you discretize it, you can study like this, and then they started looking at it. But of course, once LES became dominant, all of this went away. Nobody cared about this anymore, and it was gone. So this is it. So what we wanted to do is think about it the same way, but for combustion problems. So the point I want to make here is that if you take any boundary condition and any initial condition, so I plotted in 2 dimensions. Instead of 10 power 12 dimensions, I plotted in 2 because that's the best I can do by hand. So this is 2 dimensions, psi 1 and psi 2, okay? And for a set of boundary conditions, regardless of the initial conditions, there's only a part of this phase space that I can get to. And that's, to me, dictated by thermodynamics. So for instance, I cannot have mass fraction of oxygen and mass fraction of fuel both be 1 at the same time because there's a limit. The sum of mass fractions has to be 1. So there's a diagonal on this plane. I cannot live outside that plane. There are also equilibrium considerations. So if my fuel is at mass fraction of 1, I cannot have oxygen that's of any other value. So it's all constrained. So there's only a small region within this entire phase space where my solution can actually live, okay? So that's what I call AR, the realizable part of this phase space. And then depending on what conditions you use to solve the problem and where you are and things like this, you can have other smaller dimensions. So for instance, you can have AS, which would be the access space that you have for that particular set of conditions. And then you have this thing called A, which is the attractor. So it doesn't matter where you start within AR. They're all thermodynamically consistent. The solution will now force itself onto this much smaller region, which is this blue region A. Yeah. So if you ask this question, now you can say, it doesn't matter what my boundary conditions are. I only need to know what happens in that region, blue region A. Okay? So that's what gives me the idea of what an attractor is. And the picture you saw for the Lorentz system, that is what is called an attractor. So instead of things moving in 3 dimensions, everything collapses into 2 dimensions. It's a lower dimensional space. So that's the attractor. So this comes from many different ideas. So the original idea comes from computational finance. So there is this book on black swans. If you guys have not seen it, or read it, you should read it. It's by Nicholas Nassim Taleb. So he's written this book. So the notion of black swans is very simple. Europeans had swans long time ago, and the swans were all white in color, which I guess you guys all know it's white in color. Until you go to Australia, and then the swans are black in color, okay? So the notion is, it's not that the swans flipped color when they went to Australia. It's simply that you have not encountered yet a condition under which swans can be black, right? So that's what's called a black swan event. So you have mitigated all kinds of risks that you can expect, and so you've built a system to avoid those risks. And then comes an external shock that you did not plan for. And that shock can destroy the whole system. So when you design an engine or any kind of engineering device, you first have to have a measure of what risks you're trying to avoid, right? And once in a while, you can have a case where all of these risks go out of the way. So there are cases where, for instance, you have multiple engines on an aircraft, and none of those, all the engines going out at the same time is an extremely low probability event. But these things do happen, right? There are many cases where all engines blow out at the same time, right? So that would be like an extreme or a rare event that potentially you should decide whether you want to plan for it or not. So the black swan is a way to think about it. So in my definition of this, that that space AR contains all of those events that are potentially dangerous, but you have never encountered them because you have to start at the right place in order to see those events. Otherwise, very quickly, you'll be sucked into this A, which is the low-dimensional attractor. And in the attractor, all the events are mapped out. You have not seen any of these extreme cases ever. And so you always think these systems are going to work and nothing is going to be bad. So for that matter, when you do flame flashback, if you always run the experiment the exact same way, or you always do the studies the exact same way, you will only see a particular variation in flame velocities. Because the way you do the experiment, you reach that blue attractor very quickly, okay? But if you change the experiment and you do it a slightly different way, you take a different path in that AR, the realizable space, to get to that attractor, and now you might encounter an event where the flame is moving very fast, or there's a much higher heat load that you probably have not seen before. Okay? So this is the part of trying to understand how to look at these dynamical systems and these kinds of extreme events. So once you have this construct, you can talk about, like what I'm saying, extreme events, things you did not predict before because we are not looking for it, and also rare events, things that don't happen all the time, but when they happen, they can have very high consequences. Inlet unstart, flame blowout, or even soot formation, which is very intermittent. And so sometimes you form it and you don't form it, things like that. Okay? Now, all of this comes to us from weather prediction, where these guys have to do this every single day. They didn't predict today, which is a bad idea, but overall they do very well. So it used to be that weather prediction in the 90s was not particularly good. There were a lot of errors in the path for hurricanes and things like that. But since then, they have become very good at predicting trajectories, and much of it comes from their ability to assimilate data from satellites or other kinds of sensors, but also the use of ideas that I just talked about. How do you do these calculations so that you can predict that different divergent paths given the same data? Like, how do you know what's the width of that trajectory, right? So, because if you don't know the width, you cannot make people evacuate those regions. So you have to have some evidence for it. So these questions you cannot ask with only LES. You need to add some other layer on top of that. Okay, so I have a mathematical theory for this to look at it, which comes from, just like Kolmogorov spectrum, this is a different spectrum called the Lyapunov spectrum. And then what you do is you try to understand what is the sensitivity of the flow, like how easily can you push the flow to do things that are different from what it normally wants to do, okay? So, which means that you have a system that you continuously push in different directions, and you're trying to figure out in what direction do you need to push so that it goes the farthest away from where you started, okay? So it's a sensitivity to the initial push. You have methods that use things like adjoints and sensitivity analysis and things like that. And one of the things that comes out of this is an analysis to figure out how receptive is the system to these kinds of perturbations, okay? So there's a lot of slides after this that explain all of these features. I'm not going to go through this because it's so hard right now that I cannot talk anymore. But I want you to think about this, right? So what I find troubling overall is that much of the research, so I'm an associate editor for Combustion Flame. So I see papers most likely from all of you all the time, right? At some point, and I know many of you because I've already seen your papers, right? So what troubles me always is that the ideas are not expanding. In your mind, these ideas are new because you're new to this field. But then in my head, it's not expanding. We are doing the same things repeatedly, yeah? I'm not saying this is some great idea. This is the idea that I came up with. But think about it this way. Think about how to expand from all the theory we look for, LES or combustion modeling now. I'm sure in your own research work, you'll have different questions and so on. But somehow it has to broaden the field. Otherwise, it's going to collapse on yourself. Yeah, so that's very important. So I'm going to stop here in the interest of my own safety. I'll be here. You can come ask me questions. Tomorrow, we'll look at another topic that I deeply care about, scramjets and detonations, and then we'll go from there.